Hi and hello. Welcome to our channel named Algo Exploration. My name is Sami and today we will going to continue the finding of time complexity from the recurrence relation. In the previous video, I have shown you using the substitution and recursive tree method, but today we'll be using a master theorem. Now, before going to understand the master theorem, I'll suggest you to please watch the asymptotic notation video of big O, omega and theta that I have created previously. So let's get started now. Using the substitution or recursive tree method, we can find the complexity from any recurrence relation. But master theorem is a shortcut way to finding the time complexity from the recurrence relation. So there are some limitations. It says that if the recurrence relation is in the form of T of n is equals to A into T of n by b plus f of n, then only we can apply the master theorem, where a should be greater than equals to 1, b should be strictly greater than 1, and f of n should be a positive function. Now we have three cases here. The case 1 says that if f of n is equals to order of n raised to log a base b minus epsilon, then T of n is equals to order of n raised to log a base b, where epsilon is a positive constant. The case 2 says that f of n is equals to omega of n raised to log a base b plus epsilon, then T of n is equals to order of f of n, but we have to check the regularity conditions as well. The regularity condition is a into f of n by b should be less than equals to c into f of n. Now the third case is if f of n is equals to theta of n raised to log a base b into log n raised to k, then T of n is equals to order of f of n or order of n log a base b log n raised to k plus 1, where k should be greater than equals to 0. Now for summarization, if you know the asymptotic notation and you know the big O, omega or theta, you will know that in this equation, if f of n is equals to order of n log a base b minus epsilon, here this term is bigger than f of n, then we will simply put T of n is equals to order of n log a base b. When f of n is equals to omega of n log a base b plus epsilon, here in this case this term is bigger, so we will put T of n is equals to f of n, and when both the terms are equal, that is f of n is equals to theta of n log a base b into log n raised to k, then we can put any of this term, either f of n or n log a base b into log n raised to k plus 1. Now let's take an example and understand it clearly. The question is T of n is equals to T of n by 2 plus n square. Now is this in the form of a into T of n by b plus f of n? Yes, it is. The value of a here is 1, value of b is 2, and f of n is equals to n square, which is a positive function. Now here we are simply comparing n raised to log a base b with f of n. Now we can find this value, it will be n raised to log 1 base 2, and f of n is n square. Now this will be n raised to 0, that will be 1. So by comparing, we found out this term is bigger, so it goes to in case 2. The case 2 says that f of n is equals to omega of n log a base b plus epsilon, then T of n is equals to order of f of n. For time being, please neglect this epsilon term. In later, I'll show you why we are using epsilon term here. So the time complexity of this recurrence relation will be T of n is equals to order of f of n. The value of f of n is n square. That's it. In just a second we can find the time complexity of this recurrence relation. Now let's take another example. T of n is equals to 8 into T of n by 2 plus n square. Now the value of a here is 8, value of b is 2, and f of n is n square. So the value of log n raised to log a base b will be n log n raised to log 8 base 2, that will be n raised to 3, and f of n, value of f of n is n square. So here in this case this term is bigger, so it goes to case 1. It says f of n is equals to order of n raised to log a base b minus epsilon. Here this will be bigger, so we can simply conclude that T of n is equals to order of n raised to log a base b. So the time complexity will be order of n raised to log a base b, that is n cube. Now please observe here, value of f of n is equals to n, and the value of n raised to log a base b is n raised to 3. Now by comparing we found out that this term is bigger, so it goes to in case 1, that says f of n is equal to order of n raised to log a base b minus epsilon. So let's put this condition, let's put the value f of n is n, the value of this is n cube. So to make this equal we have to divide the right hand side by n square. It will be n cube by n square. So this term will be n cube minus 2, and this is nothing but a epsilon. It says that the right hand side is bigger than n square from left hand side. That's it. So here minus epsilon is nothing but n raised to epsilon times is bigger than f of n. Here n raised to epsilon times it is smaller than f of n. This is the significance of epsilon here. It is actually showing us how many times left hand side or right hand side is bigger or smaller. So now let's take the third example. T of n is equals to T of n by 2 plus n cube. Now the value of a is 1, value of b is 2, and f of n is n cube. So the value of n raised to log a base b will be n log n raised to log 1 base 2, that will be 1, and the value of f of n is n cube. So we can see that f of n is bigger. So simply putting, T of n is equals to order of n cube. Now since f of n is bigger, it goes to case 2. Now we have to check the regularity condition as well. Regularity condition says that a into f of n by b should be less than equals to c into f of n. Now the value of a is 1, f of n by 2 should be less than equals to c into f of n, that is n cube. Now if f of n is n cube, then f of n by 2 will be n by 2 raised to 3. So the value of this term will be n by 2 raised to 3 should be less than equals to c into n cube. Now we can see that it is satisfying. So most of the time the regularity condition will satisfy, but then also we have to check it. So let's take next example. T of n is equals to 2t of n by 2 plus n. Now this recurrence relation we have solved it using a substitution and recursive tree method. So I hope you know the answer. Now the value of n log a base b will be n log n raised to log 2 base 2. That will be n, and value of f of n is n. So we can see that both the terms are the same. So it goes to third case. But in the third case, it is n raised to log a base b into log n raised to k, where k should be greater than equals to 0. Now if we put k equals to 0, then n raised to log 2 base 2 log of n raised to 0 will be 1. This will be 1. So answer will be n. So this term and this term are equal. So the time complexity of this recurrence relation will be T of n equals to order of n into log n raised to k plus 1. So the value of k is 1. Sorry, the value of k is 0. So it will be order of n log n. So in this simple step we can find the time complexity using the Master Theorem. Now in the next lecture we will be going to start divide and conquer strategy. So thank you.